briefly explain this network design for an enterprise client that had two requirements. The first requirement was to construct a new headquarters LAN for their enterprise. Okay. The second requirement was to integrate that newly constructed HQ LAN network to two pre-existing LANs located in Bristol and Luton. These are two pre-existing branches with the respective LANs, two respective LANs behind them. The job is to integrate the newly constructed LAN to these two existing branches. Okay. To satisfy these two requirements, the first thing that was done was to create, first of all, a 3-tier campus network, a hierarchical structure, okay, so that the traffic patterns are deterministic and traffic patterns are predictable. Okay, this is the structure that's used as per Cisco best practices. On top of that, the traffic pattern is a north-south traffic pattern that happens here. Okay, it's a 3-tier architecture that comprises of access, distribution, and core layers. This was the solution for the LAN. As far as the WAN is concerned, because of the financial constraints, due to the majority of the budget being invested here in the local area network, a WAN technology that was cost effective was implemented in this particular scenario to work around the budget of the enterprise client. DMVPN, Dynamic Multi-Protocol Virtual Private Network, was implemented here to satisfy the requirement of the client whilst working in the constraints of the budget. As we can see here, these tunnels essentially are overlay tunnels that leverage the existing underlay infrastructure. As we can see here, each edge router has a point-to-point connection with the ISP. As we can see here, /30/30/30. Okay, so this is the DMVPN. So if we quickly have a look through each layer, the first layer here we have is the access layer. Okay, so if I open up the access layer, an access layer switch here, for example, we can denote a few things from these switches. As we can see, we have a console password, and we also have a privileged exec password. This is very important for security, for securing these devices. So if I just go through the run quickly and show some of the happenings here, as we can see here, service password encryption has been applied on this particular box. It's been applied on all devices to make sure that the credentials and passwords are protected. This is the locally used username that's used for SSH. This is the password for the privileged exec mode. As we can see here, these are two essential components of is an essential component of SSH. We have IPsec running to make sure that the lookups and all of the operations performed by the boxes are done in a quick manner. Right, IPsec really improves performance. If we look at some of the ports here, this is a down-facing port. This is one of the ports that's facing the end hosts. As we can see here, port security is in place. It's in play here, and as we can see, there's a maximum of 2 MAC addresses allowed. We can see MAC address sticky is the way that MAC addresses are learned. Only a maximum of 2. If any of these particular port security measures are violated, then the port will just drop all traffic from that unauthorized MAC address or end host, and it will continue to forward the traffic that's permitted, and it will also send a notification to alert the network administrators about this particular violation. As we can see here as well, as far as DTP is concerned, these ports facing the end hosts are hard-coded as access ports. Okay, there's no negotiate. We don't want dynamic trunking protocol to take place. We want everything to be fixed. We don't want any issues. So this is another best practice, as we can see here. Another best practice here is to enable, as we know here, these are layer 2 switches. Inevitably, STP is in play. The STP that's being used in this particular scenario is RPVST, Rapid Per VLAN Spanning Tree. That allows us to it's a much faster speed compared to the 8021D original flavor, and as we can see here, port fast is being used on the ports that are facing the end hosts, because we don't expect any BPDUs from the end hosts. Therefore, it's fine. In case the BPDUs are introduced there, then what would happen would be there's a guard in place to block the port and put it into error disabled mode in case someone was to connect the switch and send BPDU frames across that particular port. Here, if we analyze the port that's facing upwards, upstream towards the distribution switches, as we can see as well, it's a trunk port. 802.1q is the most common trunking process or standard. It's in play here, as we can see. There's a dedicated native VLAN for security purposes. We don't want to be susceptible to double VLAN tagging or any of these other types of attacks. So this is a wise thing to move the trunk VLAN, or the native VLAN, sorry, from the default of 1. I've moved it to 50, as we can see here as well. Non-negotiate is also in play. Another important thing that I wanted to mention was to place all unused ports on these access switches, shut them down, and place them into an exclusive VLAN. As we can see here, if I show the VLAN brief, we can see that VLAN 99 is exclusively for the native VLAN, so these are all the unused ports. This is another good security measure to put in place. And as I mentioned earlier, we have a dedicated native VLAN as well as a management VLAN. Okay, this is where the management admins can sort of log onto and connect their PCs to. Okay, so this is pretty much the access layer. High port density is important here, among other things such as port security. Okay, so now if we move on to the so this is the access point for all network devices. They all connect here. So each port is hard-coded depending on what VLAN. So VLAN 12, that port there belongs to VLAN 12. That port there belongs to VLAN 10, so on and so forth. If I move on to the distribution layer, this is where it's a very important layer. This is the aggregation point for all access switches. Okay, this is where our SVIs reside. These SVIs essentially act as gateways or as IP addresses for the corresponding VLANs that were created at the access layer. So if I quickly show the if I show the IP addresses, so I have an SVI available for each VLAN. So there's 5 VLANs in total in play. 100 belongs to management, and the rest are all user VLANs. Okay, so these are all SVIs for them, and we also have a DHCP pool up and running on our distribution switches. As we can see here, for each VLAN there's a pool. There's a number of excluded addresses, and these addresses here are excluded for a very specific reason, right? If I show the standby brief, I can quickly explain. If I show the standby brief, we can see here clearly that for each VLAN, specifically on D1, for VLAN 2, 4, and VLAN 100, this is the HSRP active gateway, okay? Whereas for 10 and 12, it is the standby. As you can imagine, D2 here, if I was to access this box, it's the opposite. So for 10 and 12, this is the HSRP active, whereas for 2, 4, and 100, the HSRP standby is this, okay? So this enables load balancing. We don't want to overwhelm just one distribution layer switch to take all of the traffic. So by load balancing the HSRP active gateway, assigning some VLANs to use this as the active gateway and a number of VLANs to use this as the active gateway, it allows load balancing and it creates for a higher performing network. Okay, now as I mentioned earlier, RPVST Plus is in play, and it allows us to also place these VLANs where the VLAN uses this particular switch as the active gateway. We can use this switch as well as the root primary. Okay, so if I bring this particular, if I show the spanning tree for VLAN 2, for instance, this is the root. As we can see here, this is the root. Why? Because it makes sense as per Cisco best practice to place the HSRP active in the same switch as the spanning tree root primary. Okay, this is for efficiency, and this applies to all of the other VLANs. For example, VLAN 4, as I mentioned earlier, is the root. However, for VLAN 10, for instance, where VLAN 10 does not use this as its main HSRP gateway, we can see that this is not the root for it. Rather, the root belongs on the other side. Okay, so syncing the HSRP gateway to the spanning tree root primary is another best practice that's implemented here on the distribution layer switches. Now, one more thing to mention about the distribution layer switches. Essentially, it is a demarcation point between the layer 3 and layer 2. What that means is everything facing down is a layer 2 port, essentially participating in spanning tree, and anything pointing up towards the core are IP address ports. So you have to apply the no switch port command and give it an IP address. It's also participating in OSPF. Okay, so that's the last thing I would like to mention about the distribution. Now, if I move on to the core, these switches are essentially responsible for routing. Okay, the main job of this is to route traffic all across the network. Okay, so as you can see here, the routes, it has the routes for all of the SVIs. It has the routes for the as we can see, it has routes for the gateway to the internet. Okay, thanks to OSPF. This, by the way, came from the command. It came from the command default information originate that was applied here at the HQ. So this exit gateway to the internet, because of the default information originate command here, it was able to be injected, and now all of the switches participating or routers participating in OSPF are aware of it. So essentially, this layer here is very simple. Its main job is to deal with routing. Anything towards the core, all the routes to the core should be summarized for higher performance. Okay, so this is essentially what's going on here. It's exclusively layer 3, no layer 2 whatsoever. OSPF, and we have ECMP going on. Okay, so now if I quickly move on to the edge router, if I show the NAT that's going on here, this is where the NAT is taking place. Okay, so this is where the NAT is happening. As we can see, we have a NAT access list, and PAT is the particular flavor of NAT that's been implemented here to translate all of the inside private addresses to this one public internet-facing IP address. Okay, of 20.20.20.2 is the single public address that's been used to translate all of the inside hosts. Now, if we look at some of the characteristics of the DMVPN tunnel interface, we can see what's happening as far as the configuration. So this is the hub. This is the hub interface, as we can see here. It's using IP NHRP redirect. NHRP is responsible for, as we can see, it's responsible for mapping spokes to dynamically to the hub and registering. Okay, we have GRE in play. Not only is it GRE, but it's multi-point GRE. Okay, it's somewhere over here. Here it is. Okay, this is very essential. We also have IP OSPF network point to multi-point. This is very essential because most networks by default OSPF are either broadcast interfaces or point to point, but this is very important so that the hub can register with multiple spokes. As far as the tunnel interface is concerned, we have some security on the tunnel. We have some MTU factorization, as well as other layer 2 factorizations to deal with the GRE overhead. Let's look at the routes coming across the tunnel. Okay, the OSPF routes coming across the tunnel. We have a few routes. These two routes belong to the tunnel itself. That's fine, because OSPF, it's been advertised, the tunnels are being advertised into area 0. Here we have two interesting routes coming across the tunnel. Both of these routes are inter-area tunnels, okay? These are the only two inter-area tunnels, i.e. they come from another area, okay? This is because behind the Bristol edge, so behind the Bristol edge and behind the Luton edge are loopback addresses that represent the local area network that would be behind these two respective branches, okay, with a /22, okay? So it's quite a big network. It's quite a big subnet, sorry. So you can see here, these two particular routes represent the LAN, okay, or the users that would be in at Bristol or Luton, okay. We can actually have a look also at one of the branch routers to see the results. Okay, so if I show the OSPF routes coming in, this router here is an area border router, so it belongs to both area 1 and area 0. Area 1 is the LAN, and area 0 is the tunnel itself. Okay, so we can see here all of these routes are coming from the LAN. Okay, all of these routes are coming from the LAN, therefore they're considered to be intra-area routes. But the only one that's considered to be an inter-area route is the routes coming from the tunnel, which is coming from Luton. This particular subnet here is coming from the LAN of Luton. Okay, so now we can test their connectivity. If I go to any one of these end hosts, okay, if I request an address, okay, it should come from the distribution layer. So I've got my address now from the distribution layer. Excellent. For VLAN 2, this is the correct subnet. If I ping the users in Bristol, okay, which have this particular IP address, excellent. So the DMVPN tunnel is working, the campus network and the HSRP and everything is all working. The NAT is working. It goes across successfully using the overlay tunnels, which relies on the underlay connectivity. Okay, there's static routes, by the way, that enable the underlay connectivity straight to the ISP. Okay, so everything's up and running. We can test as well for Luton, connectivity to Luton. If I test that again, I had some issues here. I can use another PC, no problem. So let's get an IP address for this PC as well and ping across to Luton. Excellent. So we have now successfully pinged from the headquarters, one of the end hosts connected to the access layer, all the way across to the LAN or the loopback addresses located at the two respective branches. In summary, the network design that I put together included, from a high-level design perspective, included both a WAN and a LAN, the WAN being DMVPN technology, interconnecting all three sites, as well as a LAN, which was the 3-tier campus network design. When we look at it from a low-level design perspective, I discussed some very important things, including port density, DTP, port security, in the access layer, which are very crucial. In the distribution layer, I did mention the importance of HSRP, the importance of the DHCP pool, the importance of syncing the spanning tree route with the HSRP active, as well as the fact that that particular layer is the boundary between layer 2 and layer 3. The core layer, I did mention the routing aspect of it, and that being the main function of it, to route between the different across the whole network. Okay, in the lower layer, the distribution layer, we have the SVIs that allow for inter VLAN routing, but this layer here specifically routes exclusively for the entire network. Usually the highest capable boxes or multi-layer switches are implemented at the core. We also have the NTP, which is crucial for logging. It's crucial for retrospectively troubleshooting, and it's crucial that the NTP is the same. Okay, it's consistent across all network devices in the LAN. The core one is where the NTP master is located, specifically the loopback address, so that it's up at all times. There's authentication to make sure that the NTP communication is only for authorized users. Okay, as I mentioned before, we have the routing design, essentially that extends from the area 0, which is located at the HQ, and includes the tunnel interfaces, extends across the internet through the DMVPN tunnels, thanks to GRE, towards Bristol and Luton, the two branches, which have area 1 and area 2 respectively, belonging to their respective LANs. Okay, so that was the routing design. We also have the NAT, or the PAT, should I say, which I implemented on all three edge routers, being Bristol, Luton, as well as the HQ edge. Okay, the WAN technologies included GRE, IPsec, NHRP. Okay, hub where is the HQ, and you have the two spoke routers being Bristol and Luton, and the configuration allowed for spoke-to-spoke communication, DMVPN phase 3, thanks to NHRP shortcut on the spokes, as well as NHRP redirect on the hub. Here is some of the configuration that facilitated that. And finally, moving on to the management aspect of things, we have the privilege exec password, we have the console password, we have the terminal line password, VTY password, which is used which uses the local username and secret. So this is all just to protect and to manage the device, as well as only allowing SSH as the only form of remote access that's allowed. No telnet, it's not secure enough. SSH only. Okay, and there's also a dedicated VLAN 100 for management purposes. All of the layer 2 switches in the access layer have one IP address that belong to this particular subnet. For example, A1 or A4 here has an IP address of 192.168.100.54 with a /24. Okay, so management is another aspect of things of how you manage all of the devices in the network. Now, on reflection, bearing in mind the limitations, if I was to repeat this experiment or project again with no limitations whatsoever and a free budget, then I would implement 2 firewalls at the edge of the network. For redundancy purposes, I would have 2 edge firewalls as well as 2 edge routers. The link between them is the failover link between the firewalls to ensure that the standby firewall takes over the active firewall were it to fail. You also have a dedicated DMZ for public services or public web servers or other types of servers that need to be accessed by the public, connected directly to the firewall via a switch. I also have included another server in the LAN at the distribution layer that has services including AAA for verifying user credentials, as well as syslog, which is essential for logging to understand and to keep a record of all activity on the network, as well as having a dedicated DNS server rather than relying on the public 8.8.8.8. It's better to have your own local DNS server that can resolve most queries. And in case it cannot, it can always be referred to the secondary DNS source being 8.8.8.8. So those are some of the changes that I would make. I would also include SNMP, an SNMP software on a VLAN 100 PC, on a management PC. I would include an NMS software, open source, and then I would make the network devices in the topology SNMP agents that interact with the NMS and are pre-configured to send traps in case certain thresholds are passed.